Okay, in this video I want to clarify how to figure out the number of solutions to the equation ax equals b from the row echelon form or reduced row echelon form of A. So let's say that you have a matrix A, which is an m by n matrix, right? And so this means it has m rows and n columns, and so let's say that B is a vector in Rn. And the question is, so we're solving for x in Rn, and the question is how many x in Rn solve Ax equals B? That's the question. And this is a nice summary of the reduced row echelon form. So once you find a row echelon form of A, and again, this is not unique, there are multiple row echelon forms. You can find a reduced row echelon form, but it doesn't have to be the reduced row echelon form. It just needs to be an echelon form. And so once you get the once you get a row echelon form of A, when you row reduce the augmented matrix, the vector B is also going to change. So let's say B changes to B prime. Let's say that's the vector you get. Okay. So now we have this situation where you have an augmented matrix, which is an echelon form. Well, not the augmented matrix, the coefficient part of the augmented matrix, right? When you're reducing an augmented matrix, you're trying to get this part into echelon form. It doesn't matter what this is, okay? So you make sure that this matrix, the matrix A, gets to row echelon form. Not necessarily the augmented matrix. Okay, so let's go over what happens when you have this. So first of all, okay, a system of linear equations, as long as you have real number entries, which we do, is going to have either 0 solutions, 1 solution, or infinitely many solutions. And let's say that you have a row of zeros on the bottom. Okay, these are all zeros. And you have some number here. Now let's say, so this is in the B part. Let's say this number, okay, if this number star is not 0, then the bottom equation is, let's say that you have, so this is m rows and n columns. Each column corresponds to variables. You have n variables and you have m equations. So then the bottom equation would be 0x1 plus 0x2 plus ... plus 0xn equals some non-zero number. Well, that has no solutions, right? There's no x1 through xn that's going to satisfy that. So this system has no solutions. And the system has no solutions. And when we say no solutions, I mean it has no solution at all, right? So in this case, the system is inconsistent. So some linear algebra textbooks use this terminology. Not all linear algebra books, but many of them, the standard ones, do use this term. The system is inconsistent. Okay, now what happens if you get a row of zeros in the A part, but then in the B part, right, this column, whatever it's called, some books call this the vector of constants, this vector here, right, the augmented part. Let's say that you get 0. Okay, When you have something like this, where the bottom row, including the augmented part, is all zeros, a common misconception, right, it's a misconception, is that the system has infinitely many solutions. It's not true, okay? I mean, if you look at this bottom row and think about what equation do you get from this? This equation says 0x1 plus, plus 0xn equals 0. Well, that doesn't tell you anything about x1 through xn because any x1 through xn is going to make that equation true. So this bottom row doesn't tell you anything. About whether the system has a solution or not. Whether it has a, well yeah, actually, because you could have, another 0 row here, and then you could have like a 5 here. I mean, what if you had something like that? Well, then your system would be inconsistent, right? So let's say that you don't have any of this inconsistent part. Let's say that the system is consistent, right? We know how to tell if it has no solutions. It has no solutions precisely when you get a row of zeros in the A matrix, but then a non-zero number in the B, in the augmented part. That's the only way you're going to get inconsistent. If it's inconsistent, that's bound to happen, okay? There's no other way you could somehow get it to be inconsistent. So let's say we don't have this, right? Let's say that you have consistent. So otherwise, right, to continue off what we were talking about here, so if this star number is non-zero, then the system is inconsistent. Otherwise, the system is consistent. And then the question is, how do you tell if the system has one solution or infinitely many solutions? And what you're looking for are free variables. Okay? By the way, let me give an example of a system where you're going to have infinitely many solutions in this case, and a system where you have one solution. So you're going to have something like, let's say that you could have something like that, and then zeros like this. Well, this is going to have this has exactly one solution. Okay. Because this is going to be x plus 2y equals 3, 2x plus 3y equals 5, and actually you can solve and get x equals 1 and y equals 1. And then this third equation is just 0x plus 0, y equals 0. And when you solve this, you get x equals 1, y equals 1. So here's an example where you get the bottom row is 0, but the system has exactly one solution. Now you can also have one where you have infinitely many solutions. So like if you just had this, then this equation, this system says x plus 2y equals 3. So here's example 1. Here's example 2. 0x plus 0y equals 0. Well, in this system, right, there's going to be infinitely many solutions. So you can see it's the same as if you just didn't have this row of zeros. I mean, this system is really equivalent to just x plus 2y equals 3, right? The second one. But the difference is that, well, this matrix is in an echelon form, okay? But if you got this into echelon form, this first one is not echelon form, okay, fine. You might argue, okay, that it's not an echelon form. Well, if you reduce it, then you're going to get 0, and then minus 1, so it's row 2 minus 2 row 2, and you're going to get minus 1, right? Okay, fine. The point is that this first system has no free variables, whereas the second one does have a free variable. Because you have two pivots you have a pivot here and a pivot here, whereas the second example has only one pivot there. So let's write that down. So basically you have exactly one solution. So if the system is consistent, then if there are no free variables, so i.e. that's a pivot in every column, right? Every column of the matrix, the row echelon form, there's a pivot in every column of this, then the system AX equals B has exactly one solution. If there is a free variable, so in other words, there is a column without a pivot, and those columns without a pivot in the matrix A, right, not the augmented part, but the non-augmented part, if there is a free variable, so in other words, a free column, a non-pivot column, then the system AX equals B has infinitely many solutions. So that's how to tell if your matrix, if your system has one solution, no solutions, or infinitely many. Okay, so let's just summarize. So you start off with this system AX equals B, right? You row reduce, so you set up your augmented matrix, and then when you row reduce, you're going to get this matrix here, which is your echelon form, and then you're going to get some matrix here, which is probably not going to be B anymore. It's going to be some different vector like B prime. Okay. So if you have a row of zeros, and in echelon form, all the rows of zeros are at the bottom. If you have a row of zeros and then a non-zero number here, then the system is inconsistent, obviously, because you're going to get 0 equals a non-zero number. However, if that doesn't happen, then the system is consistent. And then the question is, okay, right, if you have a row of zeros, including this part, it doesn't tell you anything. So what do you look for? How do you tell if it has one solution or infinitely many solutions? You look for the columns of your non-augmented matrix and see if there are free columns. If there's a pivot in every of these columns, then that means that the system has exactly one solution, because you can actually solve, right? So here, if you look at this matrix, you can actually solve. You can convert to reduced row echelon form, and you're going to get this, right? And then you can just say what x, so this tells you that x is 1, the second equation tells you that y is 1. And you're able to get the identity matrix in the reduced row echelon form because you have a pivot in every column of A, or the non-augmented matrix. On the other hand, when you have this, in this example, in example 2, you only have one pivot column here. The first column is a pivot column. The second column is a free column. And that corresponds to the fact that you can set the second variable to be a free variable. So here your x plus 2y is 3. And so when you set y equal to t, say, you're going to get x plus 2t is 3. And you're going to get x is 3 minus 2t. So your solution is going to be x is 3 minus 2t, y was t, where t ranges over all real numbers. And it's the free variable, it's the fact that you have a free variable that causes you to have infinitely many solutions. Okay, I hope that clarifies how to tell how many solutions a system of equations has, and how to use the echelon form to figure that out. Thanks for watching.